Hello everyone. Today we are going to present our project, and the topic of our project is predictive yield analysis for semiconductor manufacturing processes. The main goal of this project is to use machine learning to predict whether the wafer will pass or fail as early as possible based on sensor data collected during the manufacturing process. My name is Hao Jiun.
My name is Cheng-Hung Chung.
Okay, let's start. So here's the outline of today's presentation. First, we will talk about the motivation of this problem, and then introduce the dataset and the challenge we observed during the EDA. After that, we will explain our future engineering strategies, followed by model selection and methodology. Finally, we will present our results and conclude with some future directions. Okay, let's start with the motivation. Semiconductor nowadays become a much more important industry around the world, and manufacturing is one of the most complex industrial process. A single wafer needs to go through hundreds of steps, and the whole process can take weeks or even months. Now, the key issue here is yield. The yield rate directly determines the profitability of a fabrication plant. If a wafer fails at the end of the process, all the time and cost invested before that point are wasted. So the problem with traditional quality control is that most defects are detected only at the end of line testing stage. Now, the modern fabrication plants are equipped with a large number of sensors that continuously collect data. So the question we are asking is, can we use the sensor data to predict failures earlier in the process? If we can reduce waste, improve yield, and make the entire manufacturing process more efficient. So we are going to talk briefly introduce our data sets. So the data set that we use for this project is CCAM data set from the UCM Machine Learning Repository, which represent the real semiconductor production environments. So this data set contains 1,567 wafer samples and 591 features in total, including one timestamp and 590 anonymized sensor signals. And each sample is labeled as -1 if it is passed and 1 if it is failed. And our objective is to build a model that can identify defective wafer based on these sensor signals. So during the exploratory data analysis, we identified three major challenges for this data. The first one is severe class imbalance. About 93% of the sample are passed, and only around 7% are failed. So this means that the accuracy alone is not a reliable evaluation metrics because the model can achieve very high accuracy by simply just guessing everything as passed. The second one is data quality. So there are a large number of missing values in this data set, and some sensor features have more than 50% missing data. Also, some features are constant and do not provide any useful information. The last one is high dimensionality. So we have 590 features, but only like almost 1,600 samples, which can easily lead to overfitting and noisy learning. So overall, this is a high-dimensional, noisy, and highly imbalanced data set.
So, as Howard mentioned before, our data is pretty difficult to do pre-processing, so we did lots of effort on this part. So as we can see, our baseline is just remove noisy constant columns and keep 100 target correlated features. But after doing this baseline in different models, we kind of noticed that the result isn't good enough. So after some discussions with the professor, he recommend us the PCA features and the VA enhanced features. And I will talk more about it afterwards. Next slide, please. So as you can see, on this table too, this shows like our pre-processing pipeline and about how it's designed. It's based on our like tons of experience, but after building like this is our best pipeline we can get, and this shows that before the PC and VAE model output, the process before them is mostly the same. So for looking for a better output, we sublize PC and VAE as our model output at the last step of our pre-processing. And next slide, please. So uh, we're gonna talk about PCA we mentioned before. So PCA first looks at how the 100 sensor features vary together. Then it finds new direction that captures the largest variation in data. Finally, we keep the first 20 direction and project the data onto them. So PCA does not select 20 original sensors. It creates 20 new features by combining the original 100 sensors features. So this lowers the features that we need to calculate. Next slide, please. So for VAE enhanced feature representation, it is a bit like is more difficult than PCA. So at first we train the VAE on the full training set and use the latent representation as compressed features. However, this was more like nonlinear dimensionally reduction similar to PCA, but it did not like learn the normal water pattern. So later we changed the design. We train the VAE only on past wafers. The idea is that the VAE learns how normal wafers looks. If a wafer is unusual, especially a failed wafer, the VAE may reconstruct it poorly, so the reconstruction error becomes larger. After training, we calculated the reconstruction MSE for each sample and appended it as one additional anomaly-related features. Therefore, the final VAE enhanced input had 101 features. The original 100 select feature plus one reconstruction error feature. Next slide, please. So after pre-processing, we need to design our model. So on phase one, we use different libraries to build models based on our processing result, but we found like the best of four different types of model we use will be XGBoost, SVM, outlier detection. And after deciding which model we are going to use, on phase two, we designed this model from scratch. And by changing the parameters, we want to find the best result that we could get. And for test model, we choose SVM outlier model, random forest, and XGBoost for our test model. Next slide, please. So we are not talking about SVM. Yes, so for SVM, we first use the library-based version, as we mentioned before, as a benchmark. The model computes a linear score and predicts fail if the score is above a threshold. The objective have two parts. The first term keeps the boundary simple, and the second term is the hinge loss, which penalizes wrong or low margin prediction. Because fair wafers are rare, we use class weights. Pass samples have weight 1, while fail samples have weight 5. So mistakes on failed wafers receive a higher penalty. Next slide, please. We do try outlier detection because failed wafers are rare, so the text may look like anomaly decision. However, the isolation forest and one class SVM had low recall even with PCA features. This suggests that that failed wafers are not clearly separated from normal wafers as simple anomalies. Therefore, we kept outlier detection as a comparison baseline, but did not select it as a final model. So as we can see from a chart on the right-hand side, the recall is like 6%. And even though having PCA, the recall is only 13%. So this result is not very good, so we decided not to use that as our test model. Next slide, please.
Okay, so now let's look at the random forest. So random forest is a Bayesian-based ensemble method which builds multiple decision trees independently and combine their results. One advantage of random forest is that it is robust to noise and works well with high-dimensional data. But here's a theoretical advantage. In our dataset, however, random forest completely failed to detect defective wafers. The recall was zero, and which means it did not identify any failures. And I will show you the result later in the following pages. And this, and the recall was zero. This kind of phenomena will happen because the data set is highly imbalanced that we mentioned before, and random forests tend to favor the majority class due to the majority voting. So we conclude that Bayesian-based methods are not suitable for this type of extreme imbalance problem. So now we move to our main model here, extreme gradient boosting, or we will call it XGBoost in simple. So unlike random forest, XGBoost is a boosting-based model. it builds trees sequentially, which each new tree is trained to correct the error made by the previous tree. So this sequential learning process allows the model to focus more on difficult samples, which is particularly useful for detecting rare defects. So in this slide, I will explain how XGBoost learn from prediction errors. So since our task is binary classification, the model first converts the raw output into a probability using the sigmoid function here. As you can see, the first formula here. So this probability represents how likely a wafer is to be defective. Then we use the binary logistic loss to measure the difference between the predicted probability and the true label. So you can see here the second formula is the logistic loss. And to train each new tree, XGBoost computes two values from this loss, the gradient and the Hazen. The gradient is here, GI. So it tells the model the direction of the error. So for example, if a wafer is defective, but the model predict a low probability, the gradient will push the next tree to increase that prediction. The Hazen here is HI. So it tells the model how confident or uncertain the current prediction is. So when the prediction is close to 0.5, the model is most uncertain, so the Hazen will go larger. When the prediction close to 0 or 1, the model is more confident, so the Hazen will be smaller. So in simple terms, the gradient tells XGBoost which directions to correct, and Hazen helps decide how strongly to update. So this allows XGBoost to update each tree more accurately than using only one gradient information. Okay, so after computing the gradient and Hazen for each sample, the next question is how does XGBoost decide where each decision tree should split? This is especially important for the SECOM dataset because we have hundreds of sensor features and many of them are noisy or highly correlated. Instead of using traditional criteria such as Gini impurity, XGBoost use a regularized split gain formula. The goal is to measure how much the loss can be reduced if we split one node into two trial nodes. So for each node, we first sum up the gradient and Hazen of all samples inside that node. So you can see here, we can summarize all the gradient and all the Hazen. So here G is summarized the total direction of the prediction error in that node, and while H is summarized the total curvature of all uncertainty. And the score of node is based on the formula here. So let's look at the numerator here, G. So since G is the sum of gradient, it represents whether the sample in this node share the consistent error direction. So if some samples want the prediction to increase and others want to decrease, the gradient cancel each other out, and the score becomes smaller. But if many samples in the node have the same type of error, for example, a group of defective wafer that are consistently underpredicted, then the sum gradient becomes large. Okay, so and now let's look at the numerator here, denominator here, sorry. Here, H reflects the accumulated curvature information, and lambda is the L2 regularized term. So the purpose of lambda is to prevent a model from making overly aggressive splits or leaf values. This is very important for our dataset because with 590 sensor features and around 1,600 samples, the model can easily overfit to noise. So in other words, if a split only helps a few extreme samples, the regularization term reduces its score and makes the model more conservative. So the final speed gain compares the quality of the two child node with the original parent node. So here will be the formula. Okay. So GL and HL represent the gradient and Hazen sum of the left child, and the GR and HR represent those of the right child. The model will only accept the split if the gain is larger than the threshold controlled by gamma. So conceptually, this formula asks a very practical question. Does this split reduce the loss enough to justify making the tree more complex? If the answer is yes, the tree splits. If not, the split is rejected. So now I'll explain how we handle class imbalance in our model. So in our data set, defective wafers are very rare. So if we do nothing, the model will tend to predict most samples as pass in order to achieve a high accuracy, just like we mentioned before. So to solve this problem, we use a parameter called scale positive weight. This parameter increases the weight of the positive class, which corresponds to defective wafers. In terms of the formula here, this means that the gradient and Hassian value for defective samples are multiplied by a larger factor. So as a result, these samples have a stronger influence during training, and the model pays more attention to them when updating its parameters. So in other words, we are explicitly telling the model that misclassifying a defective wafer is more costly than making a false alarm. This is also why our model achieves high recall, because it is trained to prioritize detecting rare defective cases. Okay, another important technique we use is threshold tuning. So instead of using a default threshold of 0.5, we search for a better threshold based on the validation performance. So our strategy is to prioritize recall while controlling a false positive rate, because in this application, missing a defective wafer is much more serious than raising a false alarm. So in this slide, I'll briefly introduce some of the key uh, hyperparameters that adjust during the whole model. So first one is unestimated, which is control the number of boosting trees. So more trees allow models to learn more patterns, but if that is too many trees, it will cause overfitting. And the second is learning rate, just like we learned in the class. The learning rate decided the step size of each tree update. So a smaller learning rate makes the training more stable, but it also costs more times. In our cases, we choose a low learning rate together with more boosting trees. Third one is maximum depth controls the complexity of each tree. So uh, a deeper tree can capture more complex feature in iterations, but it can also overfit, especially because the SECOM dataset has many features but relatively few samples. The next one is regular data and gamma. Yep. Uh, Regular lambda controls the magnitude of leaf weight, while gamma requires a split to provide enough gain before it is accepted. Finally, the most important parameter for our problem is scale positive weight, just like we mentioned before. So since the defective wafer are very rare, this parameter increases the weight of the minority class. In other words, it makes the model pay more attention to failed wafers. Okay.
Okay, so since the dataset is highly imbalanced, accuracy alone is not reliable. A model can predict almost everything as pass and still get high accuracy. So we focus on recall and precision. Recall tells us how many failed wafers we successfully detect, while precision tells us how many predictive failures are actually failed. We also look at the confusion metric because it directly shows false negative and false positive. In this project, false negative are especially important because they mean failed wafers were missed. Okay, next slide, please. So here I compare two from scratch SVM result, PCA-based and VA-enhanced model. Uh, For PCA-based SVM, the model detected 12 out of 16 failed wafers, so the recall is 75%. This means it catches more failed wafers. However, it also produces 99 false alarms, which means many normal wafers were incorrectly predicted as failed. So PCA-based SVM gives higher recall but lower precision. And for VA-enhanced SVM, the model detected 11 out of 16 failed wafers, so the recall is slightly lower. It's 68%, but the false alarms decrease from 99 to 77. This means VA-enhanced version is more conservative and gives a better imbalance with slightly better F1 F2 scores. So the conclusion is that PCA-based SVM is better if we only care about detecting more failed wafers, but a VA-enhanced SVM is more balanced because it reduces false alarms. Next slide, please.
Okay. As we mentioned earlier, random forest achieve a recall of 0. You can see for three different data sets, the random forest perform like almost the same. So you can see like it gets everyone as the normal wafer and detect non-defect wafer out. So you can see like the precision here is 0, recall is 0, F1 is 0 as well, and rest of the data set have the same performance. So a brief conclusion for this model is that based on the confusion metric result that we see here, the recall is 0% across all data set, failing to identify any defective wafers. And due to this inability to handle the extreme class imbalance, so we decided not to do further experiment on this model. So yeah, that's for the random forest part. And for XGBoost, we conduct a total of 45 experiments. This includes like 15 parameter configuration across 3 different feature sets. And the best performing configuration uses scale positive weight equals to 12, maximum depth equals to 3, and the learning rate equals to 0.025. And the unestimated is 600, which means we generate 600 trees to train it. So as you can see, the confusion matrix here is way more better than random forest, especially for the normal preprocessing here. Yeah, you can detect like 15 out of 16 defective wafer for it, and which gives the best recall, but it is also create more false alarm here, the most false alarm here. And PCA reduce false alarm is reduce the false alarm here from 120 to 96, but it also miss more defect here. So you got 13 and 3 here. This suggests that PCA may remove some subtle defect related signals so that it can, in some degree, reduce the false alarm, but also reduce the correctly detected defect. And VIE gives a middle result, catching 14 defect and missing 2, like here. And since our goal is to detect as many defective wafers as possible, we choose normal preprocessing as the best result for recall focus defect detection. So this version. So this slide shows the final performance of our selected XGBoost model on the test set. So we select the threshold for 0.03 instead of the default 0.5. And because our goal is to prioritize recall and detect as many defective wafers as possible, on yeah, for the confusion matrix, the model correctly catch 15 out of 16 defective wafer and missing only 1 defect. This gave us a recall like as high as like 0.93, which is the most important result for this project. And the AUC is 0.82, which means the model still has the reasonable ability to distinguish between normal and defective wafer. AUC here is useful because it evaluates the model's overall ranking ability across different thresholds instead of depending on only one fixed threshold. However, the accuracy and precision are relatively low because the model also produces many false alarms here. And like in this case, 120 normal wafers are predicted as defective. So this is a main trade-off in our approach. We sacrifice precision and accuracy in order to achieve very high recall. So for semiconductor defect detection, this trade-off is acceptable because missing a defective wafer is usually more costly than flagging a normal wafer for further inspection. So to briefly summarize, random forest failed under extreme class imbalance, and XGBoost combined with class weighting and threshold tuning can effectively detect defective wafers. A feature engineering in our whole model plays a very important role, especially the normal one, preprocessor one.
Okay, so overall, there is no single perfect model by our experience. When we improve recall, the model usually produce more false alarms. XGBoost achieve the strongest recall-oriented result, so it is useful as an early screening model. And SVM was also useful as a supervised baseline for understanding the recall precision trade-off. Outlier detection was not strong enough, same as random forest, because it found wafers were not clearly separated as anomalies. And It is also unclear whether further improvements should focus on data preprocessing or model tuning uh, during our experience. Since different models may require different preprocessing strategies, therefore we focus on understanding these trade-offs rather than selecting a single best solution. And I also want to mention that we try many different experience, including SVN outlier and etc. PCA the result is still not perfect, but this also shows how difficult this data set is. There is no single best solution because after all the experience we've done, this is the presentation we show. The result is the best. The best result we got is we showed on the representation. So, and we also look through some like public examples on Kaggle, and many of them have similar difficulties with this dataset. So, our results should be viewed as an open-ended screening solution rather than a fully solved product model. So, for future work, we will focus on improving precision without losing too much recall. One possible direction is a two-stage screening system. um, First, use a high recall model to catch possibilities failed wafers, then use another model or thresholding methods to reduce the false alarms. Because of the limitation project timeline, we were not able to fully explore this stage, but our results suggest that it will be a promising direction for future work. And I guess that's all for our representation, and thank you so much for listening.
Thank you so much.
Okay.